Hello, everyone, and welcome to Astronomy on Tap, Charlottesville. So my name is Matt Pryl, and I'm going to be your host for the event, and I am going to be going as Buzz Lightyear for the remainder of the evening. And so first, I just want to cheers to everyone for joining us, and want to give a quick rundown of some of what we have on store for us. And so this is our first virtual Astronomy on Tap event, and our 9th Astronomy on Tap Charlottesville event. Over the course of the past 2 years. And so thank you to everyone for joining our first event, and hopefully you're okay with some of the hiccups that might come along the way. And so I'm gonna go ahead and start sharing some of my screens, introduce our first speakers of the night. Okay, and so just to give a quick rundown of what Astronomy on Tap Charlottesville is. And so we started and we were founded by University of Virginia grad students, specifically Trey Wenger, who's currently researching up in Canada right now, in 2018. And so the whole idea with Astronomy on Tap in Charlottesville was to just bring astronomy to the Charlottesville community in a fun and relaxed setting. And so typically these have been done at bars, which you can see in a couple of the images that we have on the screen right here. But what can be more relaxing than the comfort of your own home with some of your own drinks in hand? And so we're super happy to be able to bring Astronomy on Tap to the virtually to anyone all around the world. Okay, and so tonight's schedule, what we have on store for us with tonight's schedule, is at 7 p.m. we're going to be doing a virtual cider tasting with Albemarle Ciderworks. And so they're going to take over for about 25 minutes. They're going to give us a tour of the facility. And then they're going to go ahead and maybe show us some of the ciders that they have on store as well. And so during this whole event, I just want to make sure that you guys can follow us live. We're going to be live tweeting the event on our Twitter at AoT-Cville, and you can go ahead and use the hashtag AoT-Cville if you want to go ahead and talk to us at all through the event. But after that, we're going to go on to the main event, which is where I'm going to welcome you again, and we're going to begin our trivia portion of the night. And then we're going to get into the talks themselves. And so our first talk is going to be by UVA professor Ed Murphy, where he's going to be talking about the annual Perseid meteor shower and a guide to watching in 2020. And so the Perseid meteor shower is going to be peaking over the next 2 nights. And so this is a perfect event for you to really figure out where to look in the night sky and how to best experience the Perseid meteor shower. Following that, we're going to play a mini game, a nice fun trivia game called Spice or Ice. I'm going to let you guys try to figure out what spice or ice is until we go ahead and actually introduce the game. Following that mini game is going to be Nicole Gugliucci, aka the noisy astronomer, and she's going to be speaking on seeing the invisible sky from your backyard. And then finally, Al Wootten, aka Astral, is going to be talking about ALMA in search of origins. And we're going to wrap it up with trivia as usual and prizes at the end of the night. But before that all begins, we're going to start with a cidery tour from Albemarle Ciderworks. And so again, this is called Astronomy on Tap, so we wanted to include some sort of alcohol in the event. And so Ciderworks was lucky enough to be able to create some bundles for people to actually be able to buy cider. And so that's what I'm drinking tonight. I have some Albemarle Ciderworks cider. And just to introduce them to some of you guys that might not know where Ciderworks is, they're located about 15 minutes south of Charlottesville. Off of US Route 29. And they were started in 2009. They're making cider from apples all over the world, all over the US. And you can find more information from them at their website, albemarleciderworks.com. And so I'm going to go ahead and bring the speakers from Ciderworks on right now. I'm going to go ahead and stop sharing my screen. And so you should be able to see Anne visible from Ciderworks. So there's Anne right there.
Hi, guys.
And yeah, and so Anne, I'm going to let you go ahead and take over. I'm going to turn my video off. And Anne's going to be taking you on a tour of Ciderworks and talking about their cider for about the next 20 to 25 minutes. And so you see you guys.
Thank you. Welcome to Albemarle Ciderworks. We are a small family-owned operation, started in 2009, as mentioned before. We do hard ciders, so 100% apple ciders that are fermented. I'm going to start here by handing my phone over to my cameraman, who is my sister. So give me just 1 second for that. There we go. And we're starting off tonight with we had 2 ciders in the bundle. So just so that people can try as we go along. We're going to start off with the Jupiters, and then I'm going to take you on the tour of the production facility. Our Jupiter's legacy is...
And actually, could I mention one thing before, sorry, one thing I forgot to mention to everyone before you keep going. So there's actually a Q&A thing at the bottom right there that you're going to be able to ask questions to all of the panelists, including Ciderworks, throughout the whole event. At the end of Ciderworks session, if we have time, I'll be able to ask them some questions as well. So if you have any questions, go ahead and make sure to type those into the Q&A, into the chat, or even using Twitter potentially. We'll go ahead and try to answer those questions. So sorry, Ann, go ahead and take it away again.
Thank you very much. And we do have our cider maker, Chuck Shelton. He's going to also be around to answer production questions and questions on specific ciders. But I'm going to take you on a tour first. I just wanted to open the Jupiters if anyone wanted to join us in drinking a glass of cider. So we're going to walk through here and start at our press shed. You come over? Okay. So at Albemarle Ciderworks, we focus a lot on the apples that go in the glass. And so we're fermenting straight apple juice into a hard cider, fermenting most of them to complete dryness with no sugar added back. Jupiter's Legacy, this particular cider that I'm drinking, and some of you might be drinking with me, is a blend of over 20 different varieties of apples. It's a lot of different varieties from our farm, including some crabapple varieties, and some classic cider varieties that go into this. And so we start with a raw apple and send it up. If you'll excuse the state of our press shed, it is our off season, but send it up the elevator, which is here in the back. There is an elevator that brings the apples up and drops them into our grinder. So this machine is what turns apples into pumice, which is the ground up apples. It almost looks like a very, very chunky applesauce that gets put into here. The grinder pushes it through these grates that chop up the apples. We have two different sizes. So it pushes apples through the grates to grind them up into that pumice. From there, we then send it over to our press. So this is a horizontal plate press. Classically, a plate press would be a plate with a cloth with the pumice in it and another plate and kind of stacked up like that and pressed downward. This has taken that theory and turned it sideways. So we have a central bar here that exerts pressure back and forth between the two. The plates are in between each of these little, the hinge here. And then what Chuck is working on right now, so this, what goes in between each of the plates are these saddle bags. And so the pumice actually goes in these bags and down.
And they're Velcro together.
And they're Velcro together. There's multiple sets. And so the pumice goes in these bags. And when the arm presses close, it squeezes the juice down into the collection. Then down at the bottom here. And that is the essential start to finish in the juice, grinding up the apples, pressing the pumice. From that, we do get a lot of dried apple pulp that's left over. And so that gets knocked out of the bags to get ready for more to come in. And we do try to give that to farmers when there are farmers that need it. We had a local dairy that was taking them for their cattle, which closed down, and so we're trying to find a new outlet for that. But that pumice does really well for that. So from there, we've got...
you might just say cider to wine. So the difference between grapes and apples, you have to grind the apple, which is what we did.
So this first part here is the difference between the grapes and the apples.
This
is how you process
press
it.
is probably more suited to apple and other fruits than grapes. So it's used by a number of ciders around the country. It's produced in Buffalo, New York.
It is a popular press. There are a couple different kinds of presses that different ciders in Virginia are using, but this one is used by a couple of us. It's a good nature horizontal plate press. From there, so we have the juice now, and so we're gonna slowly, so that we don't get any motion sickness, it gets pumped into our tank room. And from here is where Chuck is the master. So the juice comes in and into our tanks. These tanks are stainless steel. They are jacketed with glycol jackets to keep the temperature at a certain point so that you can keep the fermentation temperature where it needs to be for the yeast to do a clean fermentation. We use a white wine yeast typically. We have several that we use, but they're typically a champagne yeast or a white wine yeast. And we ferment that juice to complete dryness. From there, we do filter. As you can see, we have a clear product. And so we do filter, and then we do carbonate a little bit to add a little bit of carbonation to that. There is some carbonation made during the fermentation, but that gets lost during the filtering. So the filter will come up here. Is this wonderful piece of space age equipment. This is the lenticular filter. It's got lenticular, you can do this better than I can, but lenticular paper filters.
It's a pleated paper filter.
It goes down to
We use two sizes.
5 micron.
One is 5. We use that in what we call the polish step. That's the first filtering we do. That takes out any large particulate and a lot of the yeast. And the final filters run through a 0.45 micron plated filter and a membrane filter. The membrane filter is required to get quote unquote sterility. So if you don't have sterile product going into your bottle, you tend to get fermentation afterwards.
So the paper filter is fibers that, of course, are laid on top of each other. So it's not, even though it's a 0.45 micron paper filter, it's not 100%. Whereas the membrane filter is specifically set with 0.45 micron.
The membranes are created by almost bombarding with atoms, so that the holes in them are 0.45 microns. The plated paper filter has a mesh of fiber that's averages 0.45. So that's the difference.
So we start off, from the tank going through the filter, and then we have to get it into our carbonating tank. And so that's just on the way here. So our carbonating tank holds about the same as our smallest tank, so about 600 gallons, 550 gallons. And with this, we are force carbonating with CO2 to carbonate the cider. From there, it's hooked up. As you can see, we do have it hooked up right now with a hose to our bottler.
I would say most cider is carbonated, and that's the way people like it. There are a few still ciders in the country that are very good, but it requires a certain type of apple to produce a cider that will stand up in the glass. So most cider is carbonated. Our cider is wine that's basically a sparkling wine, but it's not quite sparkling because we limit the amount of CO2 we put into it to 1 atmosphere.
And some of that's why we use forced carbonation.
If you're buying cans of what we call macro ciders, which can be good and very pleasant, you have Angry Orchard, Bullrock, Bulmers from England, Crispin. Those are carbonated probably to a higher level than what we do.
So they, but they're doing a similar process for the most part with the forced carb. So from the forced carbonation tank, we go to our bottler. So we bottle everything by hand. This bottler bottles 4 at a time. Bottles get set in here. The safety screen goes down and the lever comes down to fill the bottle. From there, we then hand cap.
That is a counter pressure filler. It's not just a bottler. It's
a counterpressure filler
There's
to keep
two openings
the,
in there, so it vents the bottle, and then it allows the juice to come in and fill the bottle. So
to keep the carbonation. And then we've
yeah.
And then we've got a capper. So this is a pneumatic capper that is not hooked up right now, but using air force presses caps onto the bottles. From there, it gets put into a little bit of storage and then it gets labeled and then put out on the shelf. And so that's essentially the start to finish on from apple to glass. Chuck has a little more information on specifics of each of the two ciders that we have tonight, as well for any questions on differences from cider to wine or any part of the production process. So we're going to switch to our computer here so that we both can fit on screen and be a little more steady. Give us 1 second.
Yeah. And if you're actually muted right now, you can go ahead and unmute yourself on the camera.
There we go. Sorry, I'm using two different devices. Are we good? Can everyone hear us? No, you're still muting. Okay.
You can. Yep, you're good.
Okay. So here we are. Thank you. Sorry for the snafu a little bit. So as I said, the first cider that we're trying here is our Jupiters. We actually are a family orchard. Chuck is my uncle. We started out as a tree nursery. So we have over 200 varieties of apples on our orchard, or in our orchard. And the Jupiters actually ends up being quite a big mix of those. So we've got, as I said, over 20 varieties in the cider, at least. It varies from year to year. But it is one of our drier ciders and is a what I would say is our flagship cider.
So all of our ciders are dry. Even our sweetest one that we're going to taste next is sec, if you're talking about French cider terms. So this one is probably less than 1 gram per liter of sugar. So all the sugar is fermenting out of the juice. So what you have is alcohol and the residual apple chemicals. There are esters and ketones. There's like 1,000 chemicals in grape wine. There's like probably that many in apples. And what we're trying to do here is preserve those in the juice. So we ferment cold. We use, like Ann said, a champagne type yeast that ferments at 60 degrees and below, which is pretty cold for yeast. If you're into ales, they start like 65 and go up. So
For fermentation.
Yeah. So it's a cold ferment. And by doing the cold ferment and adjusting the temperature down, we're able to retain some of the chemicals in there, like esters and ketones, which are fairly volatile. So if you can keep them cold, they stay in solution. So the Jupiter's legacy, like Ann said, it originated out of our orchard mix, because we have 200 and some varieties, and our first Jupiters and every one since then has pretty much incorporated all of the apples that we grow here in North Garden, and plus a few others. Like someone, I think Matt said we were nationwide. We actually get juice from New Hampshire, and that's in this cider, believe it or not. It's English bittersweet apples that don't grow well here, and they're grown in New Hampshire by Farnham Hill, and we purchase juice from them. So that's blended into this. But actually, we get juice from our apples and orchards in Virginia. We don't go outside Virginia except for the juice from New Hampshire. So just so people know.
So
Yeah, there are a lot of people, there are a lot of cideries that are getting juice from Washington State. And
So we get most of our apples. We press all of our apples here, except for the small percentage of juice that we get from New Hampshire, because that is where that can come
so
from.
anyhow, the
But there are
Jupiter's,
people-
the Jupiter's has that in it. I will say that, and that adds to the complexity.
Mm-hmm.
The way you get complexity in cider is blending. There'll be another topic later on about the single varieties, which we're big on, and there are a lot of single variety stuff that we do that have a complex flavor from one apple, which is unique.
So I do want to, because we're not quite to our time, but I do want to cover a couple more things. There was a question about how long from apple to bottle. So for us, the apples are picked anywhere from August through October. We're pressing throughout from November through March, and then we start bottling in the summer.
Yeah.
So from apple to bottle is usually 8 to 9 months. And then past that, it's based on just what's available in kind of our marketing line.
Yeah. If you were doing it at home, you can do it in 4 to 6 weeks.
Yes, but we're on a larger scale and trying to jockey with only one carbonator and one bottler and one person, or maybe two bottling. It takes us a little bit longer.
The fermentation takes anywhere from late in the season, it goes faster. So it's like 2 to 3 weeks. And then early in the season, it's 4 to 6 weeks. So, and you can control that with temperature somewhat. So that's why we have the jacketed tanks and we dial them down and temperature to slow it down. When you're fermenting slower, you tend not to blow off the esters and ketones that I was talking about. So if you're like fermenting really fast, I call that a hot fermentation, and it'll blow along with the CO2 that's going out, it's going to take the esters and ketones right out the vent with it. You have to vent whatever you're fermenting in so you don't blow it up.
So what Chuck's saying is just if you're doing it on your own, it could be a much shorter process. I did want to, before we kind of end up on our thing, I did want to talk about the second cider that was in the Astronomy bundle, which is the Palm Mary. And this one is another blend. As Chuck mentioned, we do focus a lot on single varietals. The two that were in this bundle were to kind of show our bookends, kind of our dry blend and our sweet blend. So Palm Mary is one of our sweeter blends. It's got a 1.5% residual sugar. So this cider was fermented to complete dryness. And then just before bottling, sugar was added back to bring it to 1.5%. And that just gives it a little lightness to it, a little easier to sit and sip. I would not call it sweet, but compared to some of ours, it is a little bit sweeter.
No, I call it sec. If you look up the term sec in French cider terms. For French champagne, and it's up to 2 grams per liter, 20 grams per liter. This is 15 grams per liter. So this is like demi-sec. But we don't, personally, I didn't like a lot of sweetness. So I actually dialed the sweetness down in this from our previous Palm Marys. It's actually going back up in some later versions. So it's going to be 2. But it's the sweetest we do here. So, and believe it or not, there's a large percent of the population prefers sweetness, and this one actually sells really well. So, it is one of our best sellers. And if you think it's too sweet, we got a lot of other stuff here you can taste. If it's not sweet enough, then you need to go to some other cidery that actually adds more sugar. So I will say that with the Palm Mary, so the fruit that goes into this, it does end up being a blend year to year. So again, just like the Jupiters, varies a bit year to year. The difference being the Jupiters is going to be specifically cider varieties, whereas the the Palm Mary is going to be more varieties that you could eat out of hand or find at a farmer's market. So which is known as dessert fruit. So things like Pippin and Gold Rush, Arkansas Black, and One Some. Yeah, but what actually happens is at the end of the season, what do we have left in the tanks? We blend them, and then we sweeten them to whatever level we're going to sweeten it. So For instance, this year, Palm Mary, which we're bottling right now, is very diverse, and it has a lot of Hughes Crab and Harrison in it, which is, we never had that opportunity before. So fortunately, the orchard's producing Hughes Crab and Harrison for us now, along with what we're producing more. So the 2019 Palm Mary, whenever you need to drink up all the stuff in between now and then, it's bottling and tasting very well. It's sweeter, but it has a different character than what we're drinking right now. I'll be honest with you.
So, Ann, we actually have two questions from the audience. So I was wondering if you'd be able to answer
Sure.
them.
Yes, of
First
course.
question, I guess, is a little silly, but maybe it'll give us some cool insights, is do you mash the worms right along with the apples?
So
Yes.
We do try to sort apples. So
There's not a whole lot of worms in the apple, to be honest. But yes, if there's a worm in there, it's going right in the press. So we try not to put rot in the cider.
So our process is that apples go in, stems and seeds and all, into that grinder. As Chuck mentioned, we do try to pull out the rot. And some of these apples have been stored for a little while in cold storage. So most of the worms and things have worked their way out of the apples to find warmer climates.
Well,
but
a lot of the apples that we source in have been in orchards that have been sprayed to control that. I'm sure there's worms in the apples that we produce here.
they've been filtered
honest,
out multiple times. 0.45
by the time
micron
it's
is
pressed, run through a grinder, run through the press, and fermented, there's nothing in there but alcohol and water and fruit flavors. So,
and as Nicole mentioned on the chat, worms equal protein.
well, that too, but I don't think there's a lot of protein that gets into our cider, but it's in there, but there's not a lot. And yeah, there's so many processes it goes through. Plus we run it through a 0.45 micron filter that yeast can't go through. So there's no worm going through there. And there might be worm in the original product, but I'm sorry.
They mainly get sorted out is the answer to that question. I went a little too in depth on that. And then the second question, which I see, is have you used the Albemarle Pippin for cider? And that is, the answer to that is definitely yes. We use it, we have a single varietal of the Albemarle Pippin cider that's called the Royal Pippin, which I think is, someone's drinking tonight. I saw a bottle somewhere.
I'm drinking that tonight.
There we go. And then we do use it also to blend in for our Ragged Mountain, our Royal Pippin. It goes into some of our other blends. And so
Palm Mary.
In Palm Mary, which is what we're drinking right now, it's definitely an apple that is very versatile. It has a good acidity. One of the things we didn't talk about, we have a minute or two more, is what types of apples go in cider. So we're looking for all the sugar is going to ferment to alcohol. So you need something other than just sugar in the apple to make a good cider. So you need a good acidity, or you need a good tannin or bitterness. And the Pippin just has a really great acidity for cider, and good flavor profile. And so we use it in a lot of our ciders.
Awesome. Well, thank you guys so much. You still have a minute or so left. I don't know if there's anything else you want to share. Maybe some of the people behind the scenes could link the website to Albemarle Ciderworks again. You guys will be able to find a lot of more information on all the different types of ciders that they have. How many ciders do you guys have right now, actually?
We have too many right now. We're up to 20. We just released this year. We released the Wicks and Crab for our anniversary in July.
So I want to say, we do keg some of this, so ask your local watering hole if they can seek us out.
Once they open back up.
We don't sell it like tap water, but it's a little more expensive, but it has been in bars around it. Whenever bars open back up, we hope to get back in there. So, and you can just have a glass at the bar. But anyhow, We don't do a whole lot of that. Most of ours are in 750 bottles, like you're drinking from, with a few 500s. And we intend to be here 10, 15, 20 years from now. So with your help and support.
So so we have 20 right now. A lot of those are single varietals, and we are here. We do have some shipping specials going on. Flat rates for under 6 bottles, free for over 6 bottles. And then we do have a virtual tasting coming up at the end of the month that we are excited about, which is the Wixon crab, which we just released, along with the Virginia Hughes crab and some crab chips from Route 11. So just to be fun. And so that's coming up toward the end of the month if anyone's interested. And thank you guys for having us here today. I'll be on the chat for a little bit longer if anyone has any questions, but I think we're out of time, and so I'm going to send it back over to get to the rest of the party.
Great, thanks so much, guys. That was awesome. That was a really cool tour. Yeah, so then welcome back, everyone. Welcome some of the new people. I saw we currently have 90 people joining the webinar. I saw in the chat we have people from all over the place. Some people were mentioning Arizona, New Hampshire, Charlottesville, believe it or not. And then we also have some people from Connecticut. And so it's great to see people tuning in from all over the country. And so now what we're going to be doing is we are going to be continuing on with the main event. And so we're going to dive into some of the talks, some of the trivia, and just have a fun night the rest of the night. And so I'm going to go ahead and start sharing my screen again to begin the main event for tonight. And so for those of you that didn't tune in at 7 o'clock when we began, just want to reintroduce myself. So my name is Matthew Pryl. I'm a graduate student at the University of Virginia, and I'm going to be your MC for the night. But I will be going by my stage name, which is Buzzed Lightyear. As you can tell, I'm a Pixar fan from my Toy Story ball that I have in the background right here. And so tonight's speakers, we're going to be joined by Professor Ed Murphy from the University of Virginia, Nicole Gugliucci, aka the Noisy Astronomer, and Al Wootten, aka Astronomy. And just as a quick run through again, for those of you that might not have turned in at the beginning, so Astronomy on Tap Charlottesville was started about 2 years ago with the intention of bringing astronomy to the Charlottesville community in a really fun and relaxed setting. Typically that takes place at a bar, which is why we have our ciders and other things on hand. And so we're really grateful, I'm really grateful at least, to be able to bring that to you guys in a virtual setting now. It's great that so many people have tuned in, and hopefully we can continue on with these virtual events, and maybe in the near future, maybe we could even begin continuing on with in-person events again. So as another quick run through of tonight's schedule, and so we just finished our virtual cider tasting with Ciderworks, and we're going to be getting on with the trivia right now. And then at 7:40, we're going to be, Ed Murphy is going to take over. He's going to talk about the annual Perseid meteor shower, which is going to be peaking over the next 2 nights. And so he's going to give you a really great overview of how to watch that and see a lot of cool shooting stars and meteors in the night sky. We're going to begin at 8 o'clock, the mini game Spicer Ice. I'm still not going to reveal what that is yet, but it should be a really fun one. I had a lot of fun actually creating that. Then Nicole Gugliucci is going to be joining us to talk about seeing the invisible sky from your backyard. And then Al Wootten, aka Astral, is going to be talking about ALMA before we wrap it up with trivia and prizes. And so typically at Astronomy on Tap, we collect donations to help us as Astronomy on Tap be able to afford venues for the events we put on, to be able to get some prizes and trivia. But because we're hosting this virtually, instead of us collecting donations for ourselves, we decided to collect donations that can help out our local Charlottesville and Virginia community. And so the people behind the scenes should be typing in the chat this link to be able to donate to the Blue Ridge Area Food Bank. And so the Blue Ridge Area Food Bank serves those in needs across 25 counties in 8 cities, including Charlottesville and Albemarle County in Central and Western Virginia. And especially in times like now, it'd be really great if you guys can donate anything from $1 to the $5 you typically donate to Astronomy on Tap, so that we can really make a different change in our community in this fun virtual way. Okay. And then the next thing that I want to do is we want to get a really sense of who's actually watching tonight. And so we are going to be making some polls that are live in just a second. We're going to ask some questions to you, the viewer, to find out who's really watching with us tonight. And the first question that I want to ask all you guys, and before I do that, I just want to remind everyone that you can go ahead and follow us on Twitter at AoT-Cville and use the hashtag AoT-Cville. We are live tweeting the event. Make sure to follow us on Facebook as well if you want to catch this event and other events in the future. The first question we want to ask to all of you guys is, where are you watching from? We heard some people are watching from different places in different states all over the place. And so you should have seen a poll just pop up on your screen. I'll give you about 30 seconds to figure out how that polling system works, and go ahead and click on where you're tuning in from. And hopefully this would be some cool information to see if we have people just viewing from Charlottesville. We already know there's a couple of people viewing from outside of Virginia. I know I have some family tuning in from Pennsylvania, so hopefully get a couple of outside of Virginia things as well. And so we'll go ahead and wrap that up in just a few seconds. And so if we have some votes in, Catherine, you can go ahead and share those results with all of us. Oh, and wow, and so it looks like, so you guys can see this, we have a majority of people actually watching from outside of Virginia and a couple people viewing from outside of the US. I'm sure one of those people is Trey Wenger, who actually founded Astronomy on Tap Charlottesville. He's watching from Canada. We do have a good amount of viewing from Charlottesville and Albemarle County. So it's great to see people viewing from all over the country, frankly, all over the world, if we're including people outside the US too. Very cool. All right, so let's go ahead and go on to the next question. And so we all know what I'm drinking tonight. I got some Albemarle Ciderworks cider, but we'll go ahead and ask what you guys are drinking tonight. And so you're gonna have a little less time to fill this one out. And so I'll go ahead and click that cider one for me and see what everyone else is drinking. So you just get about 5 more seconds before you can fill it out, see what you guys are drinking along with us tonight. And so we can go ahead and stop that poll and go ahead and share that. Saw some people drinking cocktails, nice. We got a lot of people drinking other, that's okay. Astronomy on Tap, you don't have to necessarily just be drinking the alcohol. Some people drinking some coffee, trying to stay up, I'm guessing, to watch the Perseids tonight. And then we got some people watching soda as well. But primarily other. Maybe I should have included some liquors and other things like that in the options as well. All right, so we'll move on to the next question. And so Astronomy on Tap, the whole idea is to invite people that range in all different types of astronomy experience. So we're curious what your type of astronomy experience is tonight. And so I am not quite yet a professional astronomer. I will be, hopefully, in November when I defend my PhD thesis. I'll go ahead and mark down that I'm an astronomy student for now. And then we can go ahead and check out those results in just a second. Thank you for the good lucks in the chat. I appreciate that. I need all the luck I can get. We got a lot of fans, a lot of amateur astronomers in the audience too, and quite a bit professionals as well. That's great. And it's also great to see a couple of the none of the above. Always trying to reach out and branch out to as many possible people as we can. So I'm glad that you guys were able to tune in tonight, and I hope you have a fun night as well. Next time, offer water as a choice. Yes, I absolutely should do that. Okay, so let's move on to the next question now. And so did you guys see Comet Neowise? So I was actually able to myself go up to the Blue Ridge Parkway, observe Comet Neowise with the naked eye. I brought up my telescope. I was able to view it with my telescope as well. And it was the first time I was ever able to see a comet personally with the naked eye. And so it was absolutely awesome to be able to see that. And so I was super, super grateful I was able to get a chance to see that. And so let's go ahead and see what the results are for this one. Ooh, we got a majority of people that were actually able to see it, so that's awesome. Unfortunately, a couple of you guys won't be able to see it. If you wait around a couple of thousand years, you might be able to see Comet Neowise again, but hopefully we'll be able to see another comet in the near future. All right, so let's go ahead and move on to the last question then before we move on to the trivia. And that is, do you plan to see the Perseids? And so the Perseid meteor showers are peaking over the next 2 nights. Will you get a chance to be able to see the Perseids? Hopefully everyone tries to make at least some attempt, and hopefully they put on a good show for us tonight. And so we can go ahead and see those results then. Awesome. So it looks like a lot of people are going to try to see it. Hopefully you guys will be able to see it from home. I know typically whenever I just go out and observe the stars on a random night, just lay on my back, I'm typically able to see 1 or 2 shooting stars over the course of an hour or two. Highly recommend you guys doing that. The best way to observe the night sky is, of course, laying on your back in the grass. So go ahead and try that out. You should be able to see, hopefully, a good show over the next 2 nights for the Perseids. All right, so then, so now we're going to move on to the main trivia. And so typically at Astronomy on Tap for in-person events, we have a lot of fun trivia that we can do. And I want to give a shout out to Molly Finn and Allison Matthews, who created the trivia for us tonight. And so what you guys can do is we've created a Google form for the trivia that should be sent to the chat right now that you guys can type in. And you can also follow this link as well. And it'll bring you to the trivia where you'll have the option to potentially win some of these prizes. And we're going to have to take some of those donations you've given us over the past couple of in-person events to actually be able to ship this to you guys potentially anywhere in the country. Maybe not necessarily anywhere in the world, but potentially anywhere in the country. And you can go ahead at the end of that Google form, you just fill out your email address and we'll reach out to some of the winners. And additionally, we'll also reach out to some random people, because we always like to give some random prizes away during our in-person events. I'm just going to quickly run through the trivia for all of us once before we move on to the next section. And so our first question is going to be, missed seeing Comet Neowise this July? Don't worry, it'll be back in how many years? Question 2, many trillions of particles speed away from the sun as the solar wind. How much mass does the sun lose each second? And before I forget, I should remind you guys that you actually can get a trivia hint at our Facebook page. You can go ahead and still do that right now. Additionally, we are using the honor system tonight, so make sure not to Google any of these answers, but you are allowed to use our Facebook page for some of those trivia hints. Question number 3, which of these constellations is not part of the astronomical zodiac? Question 4, SpaceX's Dragon capsule is named after which fictional creature? Question 5, if the Earth were the diameter of the rotunda, so if you shrunk the Earth all the way down to the diameter of the rotunda, the sun would be 1.6 miles in diameter and located at which location? Question 6, in the constellation Perseus, some depictions show him holding the head of what enemy? Question 7, ALMA is the name of an observatory, but it also means what in Spanish? In question 8, Carl Jansky observed the first cosmic radio waves in 1932 by accident. While trying to minimize static radio in his antenna, he observed what astronomical object? In question 9, the discovery of Neptune is credited to Johann Galli in 1846. However, Galileo observed Neptune in 1613. But why doesn't he get credit for the discovery of Neptune? And then wrapping up the final question, astrological ages are not clearly defined, but one interpretation says the dawning of the age of Aquarius, happened when the first 6 planets, the sun and the first 6 planets, the sun and the moon, all aligned with the constellation Aquarius. What was the date of the dawning of the age of Aquarius? And so again, you guys can check out that the trivia link that was linked in the chat and go ahead and fill that out. Make sure to fill that out by the end of the event. By about 8:50 is when we'll be closing the poll. And so make sure to submit your responses then. But so what I'm going to do now is we're actually going to go ahead and turn over the event to our first speaker of the night. And so that is going to be Ed Murphy. And so Ed Murphy, in addition to being a professor at the University of Virginia, is very heavily involved in a lot of the outreach in the Charlottesville community, including leading some of the public nights at McCormick, things like that. And so Ed is going to be talking to us tonight about the Perseid meteor shower and some of the best advice for observing it in 2020. And so Ed, if you can go ahead and turn your video on, unmute yourselves, and then you can go ahead and also share your video.
Oh, thank you so much, Matt. So thank you everyone for coming out tonight. And I'm here tonight to tell you a little bit about the Perseid meteor shower, which is probably the most watched meteor shower of all. It's not the strongest meteor shower, but it is a strong meteor shower that occurs in the warm summer months, which makes it a great time to get outside and see just a spectacular celestial event. So this is a picture of what the full duration or a full night of the Perseid meteors looks like. This is taken from down in the southern hemisphere, but this is an exposure of about 4.5 hours, showing you dozens of Perseid meteors streaking through the sky. Typically, of course, you won't see.
Ed, can I just cut in real quick right here?
Sure.
So it looks like you haven't quite shared your screen with us yet. We can't see any of the slides at the very least. So if you want to go take a second, share that. Awesome. So we can see the screen. Oh, now we can't, but we were able to see it for just a second. Yes, now we can see the screen share. Okay, you can go ahead now, Ed.
And how about that?
Yes, that works. Perfect.
Okay, terrific. Sorry about that. All right. So this is a picture again from the Southern Hemisphere showing you about 4.5 hours of the Perseid meteor shower. So it's showing you a couple dozen meteors streaking through the sky. Of course, what you'll typically see is one meteor at a time streaking through the sky. And a meteor typically takes much less than a second to streak across the sky. If you look very carefully in this real-time image of a Perseid meteor, you'll actually notice that there are two of them. There's a little faint one over here that you can see just before the bright one appears. So I thought we'd start by talking about what is a meteor to begin with. Meteors are also known as shooting stars. It's a terrible name. I really don't like the name shooting stars because it gives children the misconception that what they're seeing are stars falling from the sky. And of course, we know that's not true at all today. Stars are massive, much bigger than the Earth, so they can't fall through our sky. What meteors are little tiny pieces of rock and dust and ice that are burning up in our atmosphere. And a typical meteor is traveling at about 7 to 45 miles per second. That's 11 to 72 kilometers per second. You know, in a number that you're probably more familiar with, that's between 25,000 and 160,000 miles per hour. That's how fast these little tiny chunks are traveling. And when they're traveling that fast, they contain a tremendous amount of kinetic energy, or the energy of motion. And that's what creates the light that we see. As they enter the Earth's atmosphere, they compress the air in front of them, and it heats up that air to tremendous temperatures. And the glowing streak that we see is actually the heated air, the ionized air. It's fluorescing, just like a fluorescent light bulb does, as that particle streaks through the atmosphere. Now, most meteors that you see in a meteor shower are burning up between 50 and 75 miles above the surface. That's 80 to 120 kilometers. And the typical meteor that you can see in a meteor shower is about the size of a little chunk of granola. So the next time you're eating granola cereal and you look down at your bowl full of little chunks of granola, realize that that's the typical size of a meteor particle that you're seeing burning up in the atmosphere. They range anywhere from about 1/10 of a centimeter up to about 1 centimeter, and anything bigger than 1 centimeter ends up being really bright, but fairly rare during a meteor shower. So that's what meteors are. So what is a shower then? If those are meteors, what's a shower? On a typical night, you'll see between 5 and 10 meteors per hour if you're out under dark country skies. And we call these sporadic meteors because they're coming from all directions. A meteor shower is what happens when the Earth passes through a stream of particles that are left behind by a comet or an asteroid. And as the Earth plows through this stream of particles, we get a series of meteors, typically hundreds in a given night, all streaking from an individual part of the sky. Now, the meteors, as you can see in this photograph, all seem to radiate out of a single point, and we call that point in the sky the radiant of the meteor shower. And it's the radiant that gives the shower its name. So what we have going on in August is the Perseid meteor shower. So the Perseid, the radiant for the Perseid meteor shower, is in the constellation of Perseus, the hero up there in the sky. So we also have the Leonid meteor shower, which the name comes from Leo, the Geminid meteor shower, because the radiant is in Gemini. So this time of the year, the Perseids are radiating from Perseus. Now, Perseus this time of the year is just rising up in the northeastern sky about 9 p.m., but you really have to wait a couple hours later. The meteor shower doesn't really get going until about 11 o'clock in the evening, and it's really at its strongest from about midnight to 4 a.m., and it's actually at its best from about 2 a.m. to 4 a.m., and you'll see later on in the talk why that is. But just keep in mind that meteor showers, the vast majority of them, are much better late at night in the early morning hours. Unfortunately, they don't tell you that on the news. When they tell you to go out tonight and watch such a meteor shower that'll be visible in the sky tonight, Most people go out around 8 or 9 o'clock in the evening, look up in the sky, and they don't see much. And that's because all meteor showers are best in the early morning. So why do the meteors seem to streak from a given point in the sky from that radiant? Well, it's a trick of perspective. The meteors are actually all following parallel paths to one another. But as we streak towards them, as the relative motion of the Earth and the meteor stream, as the Earth plows through these meteors, it looks to us like the meteors are coming out of a single point. You can see with this picture on the right-hand side here with the railroad tracks and the telephone lines and the top of the trees, all converging on a distant point. That is the same thing going on with the meteor shower. The meteors all appear to come out of the radiant, but in truth, they're all traveling along parallel paths. You may have experienced this if you've ever driven in a car during a snowstorm. During a snowstorm, it appears to you that all the snowflakes are coming out of a single point that happens to be right in front of you in the direction that you're traveling. Now you might wonder, how do we get a stream of particles that the Earth can pass through? And well, that has to do with comets. So this is comet Neowise. It's still barely visible in the sky. It has faded significantly since when we saw it a few weeks ago. So I was pleased to see that a lot of you got to see comet Neowise, but it was really quite a spectacular comet. I have to say it's probably the best comet in the Northern Hemisphere since Hale-Bopp back in 1997. But a comet typically has two tails, a long, perfectly straight tail called the ion tail, and then a slightly curved, typically yellowish colored tail that's called the dust tail on it. So what happens with this is as the comet, deep down here in the center of the comet is the nucleus of the comet. And the nucleus of the comet is the dirty snowball that makes up the comet. It's typically made of water ice, mixed with little tiny pieces of rock and dust and lots of other ices as well. Ammonia ice, carbon monoxide ice, carbon dioxide ice are all frozen into this ancient relic of the formation of our solar system. Comets are typically on highly elliptical orbits that take them close to the sun, then far out in the solar system where they spend most of their time, and then back into this close to the sun for a short period of time. As the comet is close to the sun, the heat from the sun will warm up the comet and the comet will sublimate. The ice will turn directly to gas, and in that process, it will release little tiny chunks of dust and rock that were incorporated in the ice. This is a picture of Halley's Comet from 1986 taken by a European spacecraft that flew by Halley's Comet. And you can see a couple of spots, they call them jets, on the surface of the comet, where material is literally jetting off the surface of the comet. As this material jets off the surface, it'll carry those little tiny particles of rock and dust with it, and they will remain in the same orbit that the comet is in. So I mentioned the comet has these two tails. The ion tail, which is typically perfectly straight and points directly away from the sun, usually consists of individual atoms and molecules. Atoms and molecules are so small that the wind from the sun can blow them directly away from the sun. And that glow that we see, typically that bluish color, comes from molecules, excited molecules in the tail of the comet emitting that light. The yellowish colored tail, the curved dust tail, consists of those little tiny particles of rock and dust. And it's yellow in color because they're typically reflecting the sun's light. So it's yellowish white in color. And those little tiny particles of rock and dust will continue in the same orbit that the comet was in orbit around the sun. So as the comet orbits around the sun, it releases these particles, and these particles stretch out. They literally stretch out around the orbit of the comet. Now, all comets do this. All comets have these trails behind them. If the orbit of the comet intersects the orbit of the Earth so that the Earth flies through this debris trail, then we get a meteor shower. And a meteor shower is visible every year at the same time of the year, because as the Earth goes around the sun, every year at the same time, we'll pass through that trail of debris. So in the case of the Perseid meteor shower, the comet is called Swift-Tuttle, and we pass through that debris trail on the night of August, typically on the night of August the 12th of every year. So Swift-Tuttle is the parent comet for our meteor shower, for the Perseid meteor shower right now. Swift-Tuttle was discovered back in 1862 by two American astronomers, Lewis Swift and Horace Tuttle. Comets are still one of the few things that we name after the discoverer. Most objects that are discovered in astronomy today are just given prosaic catalog numbers, but we still name comets after the discoverers. So this was discovered by Swift and Tuttle back in 1862. Just a couple years later, an Italian astronomer by the name of Giovanni Schiaparelli, who's famous for discovering the canali on Mars, Schiaparelli noticed a coincidence between the paths of a number of the particles that created meteor showers and the orbits of a number of comets. And he was able to associate this 1862 comet with the particles that make the Perseid meteor shower. Now, the original orbit that they determined in 1862 said that the comet would return sometime between 1979 and about 1983. The orbit was fairly uncertain because it's a very elliptical orbit. The comet goes way out, well beyond Pluto, out in our solar system. But by 1983, the comet had not returned. And astronomer Brian Marsden noticed that a prediction had been made in 1902 that this comet was the same comet that was seen in 1737. And he calculated that if that was true, the comet should come back in 1992. And so throughout 1992, astronomers were looking for the return of this comet. It was spotted in September of 1992, and it passed closest to the sun in December of 1992. Now, the orbit of this comet, the orbital period is 133 years. So it takes 133 years to orbit the sun again, a single time. And that means it won't be back into the inner solar system until July of 2126. So I'm afraid we're not going to get to see it again. Its orbit takes it just inside the Earth's orbit around the sun. So when it is at its closest to the sun, it's 0.95 astronomical units from the sun, where an astronomical unit is the distance from the Earth to the sun. So it gets closest to the sun just inside the Earth's orbit. And at its most distant, it's about 50 times further from the sun than we are. And that's much further than Pluto. So in that 133 years, it goes all the way from our orbit around the sun to well out beyond Pluto, back to our orbit around the sun. And it spends the vast majority of that time out in the far reaches of the solar system. Now, Swift-Tuttle happens to be a bigger than average comet. It's actually about 16 miles in diameter, which is about 26 kilometers across. And that's even bigger than Halley's comet. And the vast majority of comets are typically less than half that size, or about a quarter of that size. Now, one of the things you can imagine about Swift-Tuttle, if its orbit carries the particles so that the Earth passes through this stream of debris, that means that the comet also passes close to the Earth. And Swift-Tuttle is classified as one of those dangerous objects that makes close passes to the Earth. Now, we can predict fairly accurately for the next few thousand years the orbit of Swift-Tuttle. And although it will have close passes to the Earth, none of them are close enough that we have to worry about an impact with the Earth. But what makes Swift-Tuttle so dangerous is not just its close passes to the Earth, but its tremendous size. It's probably twice the size of the object that killed the dinosaurs, and it's traveling much faster. So it would have a lot more energy than that object had. But as I said, we're safe through at least the year 4000. So if you're interested in looking at the orbit of the comet, this is how the comet, this is in 2126, when the comet passes into the inner solar system again. So you can see the Earth down here traveling on its orbit around the sun, and you will see that Comet Swift-Tuttle is on a highly inclined orbit. It's tilted tremendously, 113 degrees with respect to the other planets, and it's also on a retrograde backwards orbit. And because it's on a backwards orbit, that means that when the Earth meets these particles, the Earth is traveling 30 kilometers per second, or 18 miles per second in one way. The particles are traveling in the opposite direction, and that means they hit us with a tremendous speed, head-on speed.
Hey, Ed, I just want to chime in just to let you know that you have about a minute or two left before we move on to questions.
Thanks, Matt. So the Perseid meteor shower, why is it special? Well, it's special for a couple of reasons. It's special because it's a regular, strong meteor shower. By regular, I mean that we get strong activity from August 11th to the 13th every year. And this year, it's peaking in the morning hours of August 12th. Now, we can see meteors best after midnight because as the Earth is orbiting around the sun, the side of the Earth that is facing in the direction that the Earth is traveling, that's where you're going to collect most of the meteors. It's very much like the bugs on your windshield. When you're driving a car, most of the bugs will end up on the front of the windshield and not on the back side. So between sunset and midnight, we get very few meteors, and between midnight and sunrise is when we get most. The Perseid meteor shower has a typical rate of about 100 meteors per hour. That's across the whole sky. Typically under a rural moonless sky, most people will see about 50 per hour. If you're in suburban skies, that'll drop to about 20 per hour. And in urban skies, you'll only see about 10 per hour. And the Perseid meteors are bright and fast because we're hitting this thing head on. They're traveling about 132,000 miles per hour. And one thing that's special about the Perseids is fireballs. Exceptionally bright meteors are really common with the Perseids. So to go out and see them over the next couple nights, you just want to face northeast, go out after 11 o'clock. You don't need a telescope. You don't need binoculars. Just get to as dark a sight as you can and just look up there in the northeastern sky. You don't have to stare directly at the radiant. In fact, you're better off staring higher up in the sky and just sitting in a lawn chair looking back and waiting for the meteors. This year, we do have a last quarter moon, and that is going to light up the sky a little bit, and it's going to make it a bit harder. So I think we're probably down in that 10 to 20 meteors per hour range. So that's how to see the Perseids this year, and that's a little bit about the Perseid meteor shower. I'm happy to take any questions.
Great, thanks so much, Ed, for an awesome presentation. You can go ahead and stop sharing your screen. You can get a sort of like side-by-side view as I ask you some of the questions as they go along. And so the first question that we have, and we have only about 4 minutes for about 5 questions. And so my video just came on. If you haven't seen, I have assumed my true Buzz Lightyear form as I'm about 2 to 3 drinks of cider in. But so the first question is, how are the sizes of meteors known? How do astronomers know it is the size of a piece of granola?
So what we can do is from the amount of light that we can see that comes from a meteor, we can estimate the energy of them. We know how fast they're traveling. And so then once we know their energy and how fast they're traveling, we can use that to derive their mass. And we know the typical densities of comets and cometary particles. And from those typical densities, we can estimate a size. So we start with how much light we see, which tells us the energy that's released from, and we know the speed. So we can use that to determine the mass, and the mass tells us the size.
Okay, awesome. The second question was, what causes meteor storms, and can they be predicted?
So there's only a couple well-documented meteor storms in history, and they're mostly associated with the Leonid meteor shower, and those storms occur, the Leonid meteor shower is really good about once every 33 years when its parent comet comes to the inner solar system. But there were spectacular storms in 1833 and 1966. We can predict the storms fairly well today. Unfortunately, we know that the next time the Leonids are strong in 2032, 2033, the comet is not in a good position. We're not likely to get a really good storm.
Okay, cool. All right, question number 3 then was, we still got a couple more minutes. Is there a correlation between the strength of a meteor shower and how recently the parent comet passed through the inner solar system?
Yes, absolutely. So the Leonids, again, are the most famous case of this, where when the parent comet, which is Tempel-Tuttle, is the parent comet of the Leonid meteor shower, when it's in the inner part of the solar system, and if the Earth's orbit intersects one of the streams that was released, not on this passage, but the passage before, the passage after, we will typically get a very strong meteor shower. And for some of those storms, the storm in 1833, they were recording tens of thousands of meteors per hour in the night sky, to give you an idea of what a meteor storm is like.
Wow, that's super cool. That'd be awesome to see. All right, so I think we have time for one more question, and Ed will be able to answer some of those questions in the chat as well, and so you guys can keep the questions rolling in. But the final question would be, are comets or asteroids generally regarded as a worse danger to life on Earth?
You know, it's a great question. I would argue right now, and I think some of my colleagues might differ with me, that comets are probably the bigger danger in principle because we have mapped most of the large asteroids, the vast majority of large dangerous asteroids we have mapped in the solar system. The danger with comets is they can come from deep out in the Oort cloud or are on orbital periods of thousands of years where we've never seen them before. And so We know what asteroids are out there, and we know which ones are dangerous, and there are none that present a significant danger to the Earth right now, none at all. But comets are a bit of a mystery because they can appear out of nowhere. So I would argue they're the bigger danger right now.
Awesome, great. Well, thanks, Ed, for a really cool presentation. Hopefully I and everyone else viewing from around the US and maybe around the world has a chance to see the Perseids either tonight or tomorrow night or the next couple of nights. And yeah, thanks for a really great presentation.
Oh, sure. Thank you. Thanks, Matt.
All right, so now what we're gonna do, and so Ed, you can go ahead and turn your video off, thanks. And so what we're gonna do now is we are gonna be moving on to our first mini game of the night, and that is going to be the mini game that I have been hyping up over the course of the past hour, and that is, of course, Spice or Ice. And so how does the game Spice or Ice work? Well, pretty much what you guys are gonna be doing is I am going to be showing a word, and it's either going to be a type of spice that we use here on the Earth in foods, or it's going to be an object in our solar system that contains ice. And so Ed talked for a little bit about some objects that have ices, like comets. They have water ice and dry ice and other things like that. And so we're going to go ahead and see how well you guys know the difference between a spice or an object with ice. And I just want to remind everyone, of the donations link again. If you guys can go ahead, any donations to the Blue Ridge food drive would be very much appreciated. And then also we have the link for the main trivia here at the bottom. So you still have about an hour to fill out the main trivia. And so the way that Spice or Ice is going to work is I'm going to give you this word. So for example, Pluto, you guys are going to think, Pluto, is that a spice that we use on the Earth, or is that an object that has ice? And so after that, we're going to send a poll where you're going to be able to submit your answers. And of course, the answer will be ice. So Pluto, this is a great picture from the New Horizons spacecraft, took of Pluto. Pluto has a bunch of different ices on its surface, including water ice, methane ice, and other types of ices that we are able to observe on Pluto. Then on the other side, another example is paprika. Is paprika a spice or an object in the solar system that has ice? It turns out that it is a spice, of course. But this is where the easiness of this game stops. It'll get much more challenging. You guys have five attempts. And what we're trying to do is, as a team, so typically at Astronomy on Tap events, as a team, we'll use our applause to choose during these mini games, one answer or the other. But you guys are going to choose with your votes whether you think the following objects are spices or ices. And so if we get more than half of those right, we're going to choose a bunch more random people that submit their trivia to submit some prizes too as well. And so the first one is kokum. Is kokum a spice or an ice? I'll give you some time, about 20 to 30 seconds to think about it. Discuss it with those that you're sitting around with, or have an internal dialogue in your own head, sitting by yourself like me, and determine whether kokum is a spice or an ice. And I will not submit an answer because I know the answers. And so you have about 10 seconds left to submit your answer. So get that in and make sure you hit the submit button. And we have 100 people viewing right now. So thanks to everyone that's viewing. And so Catherine, we can go ahead and show the results. Do you guys think that it is a spice or an ice? 62% think it is a spice, and you are correct. So kokum is an Indian spice that's actually not really even common in India. And it's known for its souring nature. So you guys are one for one, I guess. So the next one we're gonna move to is gong. Is gong a spice or an ice? And so again, you guys have about 15-20 seconds to discuss it before you go ahead and submit your answer. And while you're thinking, I will go ahead and have another sip of the cider as I go deeper and deeper into my Buzz Lightyear form. All right, and so time's running up, and Catherine, you can go ahead and show the answer. Do we think it's a spice or an ice? Somehow we have a 51 to 51% tie. So ties will say result in an incorrect answer. And so that means that you as a team were wrong. But the answer is ice. And so Gong is actually, it's a likely dwarf planet, not quite yet a dwarf planet, but likely a dwarf planet that's about the size of Pluto's moon Charon, and it's located beyond Neptune. A lot of trans-Neptunian objects and objects in the Kuiper Belt and the Oort cloud have a lot of these ices that we're able to observe in our solar system. It gives us some information about the formation of the solar system. All right, so question number 3. So you guys are 1 and 1 right now. 1 correct, 1 wrong. Anardana. Is Anardana a spice or is it an ice? So you guys have about 20 seconds to submit your votes for this one. And Spice or Ice is obviously, I'm sure you guys have heard of the game. It's sweeping the nation. I know it'll probably start taking off. You'll be able to see it on TV shows all over the country, I'm sure. And so you have about 10 seconds left to submit your answer. And we can go ahead then and show those results. And so everyone thinks that Anardana, the majority says that Anardana is an object that has ice, and that is incorrect. So Anardana is a spice. It is a spice created actually from dried pomegranate seeds. And it also works to sour foods. And so I'll keep in mind that we had a tie back in the second question in case you guys need some help to get over the 50% threshold. But question number 4, Varuna. So you guys are 1 for 2. You got to get the next 2 right, unless I change the results at the end. So Varuna, is Varuna a spice or an ice? These are some of the most hard-hitting questions that we have in astronomy, at the forefront of some of the greatest, what the telescopes are trying to find, whether an object's a spice or an ice. The James Webb Telescope is sure to be observing back at the Earth to detect as many spices as it can from all over the Earth. And that is a joke, just to be clear. All right, so Catherine, we can go ahead and show the results for Varuna. And everyone says overwhelmingly that Varuna is an ice. And you would be correct. So Varuna is another possible dwarf planet, this one located in the Kuiper Belt. And the cool thing about Varuna, and so just to be clear, this is an artist representation of Varuna, but it has an elongated shape due to its rapid rotation. So we've observed and detected its elongated shape just from telescopes on the Earth and orbiting the Earth as well. All right, so the final question, you guys are 2 for 2. You got to get this one right. It all resides on this final question, and that is Sedna. Is Sedna a spice or an ice? And this is for all the marbles. And by marbles, I mean some of the prizes that we have. All right, so we can go ahead. I think everyone's probably had enough time for that. You go ahead and show whether Sedna is a spice or an ice. And you guys guessed ice. And so are you correct? Yes, Sedna is an ice. In fact, Sedna is a really important object with ice that's located about 3 times as far away from as Neptune is from the sun, or about 85 astronomical units, where 1 astronomical unit is the distance from the Earth to the sun. And so observations of Sedna, which you can see with the orbits right here, actually played a really important role in this prediction of Planet 9 that you guys might have heard of from a couple of years ago. And so the orbit of Sedna and some other objects in the outer solar system suggested that there was some object gravitationally tugging and pulling on these objects like Sedna, and gave clues that maybe there was another massive planet way out in the distant solar system. So you guys did it, congratulations. You knew that you were 3 for 2 and guessing whether objects were a spice or an ice. And so I hope you enjoyed that game. And so what we're gonna do now then is we're gonna move on to our second astronomy talk of the night. And that is gonna be by Nicole Gugliucci. And so give me 1 second right here. Dr. Nicole Gugliucci, aka the noisy astronomer, is actually a a recent grad from a PhD from the University of Virginia in astronomy. She got her PhD in 2012. And currently, she is a physics professor and education researcher with a background in radio astronomy instrumentation. And she's a professor at a college in New Hampshire. And so thankfully, because of the virtual event, she was able to join us for Astronomy on Tap Charlottesville virtually. And so Nicole, you can go ahead and show your video and unmute yourself. We can go ahead and get started with the presentation.
Hello, everyone.
Hello, Nicole.
Hi, can you hear me okay?
Yes, we can hear you, but we can't quite see you yet.
Uh-oh. I have my video on, and I'm gonna try the screen share next. Oops. Hello, everyone. Good to be here virtually. I do miss Charlottesville quite a lot. I'm now in New Hampshire, which, as I understand, some of your cider apple juice is from, which is very exciting. All right, let me get this. See if I can get this right this time. We have slide, and then we have.
Looks all good from our end.
Awesome. All right, cool. All right, so I want to talk a little bit about a couple things that I love dearly. One of them is radio astronomy. I love it so much. You say recent, it doesn't feel recent. I feel a lot older than that. But I did finally celebrate getting my PhD in radio instrumentation with a tattoo many years after the fact. So I love radio astronomy. And I love citizen science, community science, amateur astronomy. I like people building stuff. So kind of bring these together to talk about a couple of different projects that you could try at home. Oops. There we go. So the inspiration for this, for me, is a man by the name of Grote Reber. So in your trivia, there's a question about Carl Jansky, who discovered radio waves from the cosmos. I'm not gonna give away the answer there. But his discovery, it made some headlines. It was really interesting, but it didn't really get followed up until a man by the name of Grote Reber followed it up on his own in his spare time. So he is, in my mind, one of the coolest citizen scientists. He was an engineer by day, and he built this dish, this radio telescope in, I don't remember if it's either a field across from his mother's house or backyard, something like that, but in his spare time. So he was like working all day and then using this radio telescope all night to look for radio waves from the cosmos. And he ended up mapping the galaxy and doing all this cool stuff. So there's a great legacy and a great history here when we talk about doing radio astronomy from your backyard. One of the simplest ways, really timely, given that you just heard about this in Ed Murphy's talk, is it's possible to detect the effect of meteors coming through the atmosphere with a radio. You can use a simple FM radio, like I'm showing a little, generic graphic of on the right. But there's also a group called Space Weather Radio that they actually have a big antenna that they use to detect meteor shower sounds. It's not, super exciting. It's a ping from reflections off the meteor trail in the atmosphere. So one way you can do it, you can kind of tune your radio to an FM dial, like in between stations where you just barely hear a distant station, and listen for the static or the noise jump up. So that's one cute little way you can get into the Perseid meteor shower, even if you are, say, clouded out and can't go outside and see them yourself. The next step up is a little tool called the Itty Bitty Radio Telescope. There are lots of, if you just Google Itty Bitty Radio Telescope, you'll find lots of instructions on how to build one. A lot of them, and the lessons come from the National Radio Astronomy Observatory. simplest thing, it's a satellite dish. I think I've conveniently scratched out the logo on that one. But it's a TV satellite dish, which you can get for free on Craigslist because lots of people just have them and don't want them. Or you can let your coworkers know and you will come to your office and find several of them sitting in your office, as has happened to me a couple of times. But super easy, free. There you can use a satellite detector on the back end. Some of the older ones, you have to do a little soldering yourself to get the power supply connected. And that's really cool for a student project if you are just teaching someone how to solder for the first time. So they actually feel like they're getting their hands dirty and building this. So you can use an itty bitty radio telescope to see a few things. See if this video works on here. I don't think I hit sound, did I?
You can hear it.
Oh, you can hear it. Awesome. So when it's, so the satellite detector there, when it sees something that is bright, the pitch of the noise goes up. So it goes the wee. So I was tilting it onto and away from the sun. Sun is pretty much the only astronomical object you'll see with that, as far as I know, because it's not super sensitive. However, there are some folks who have built more sensitive and more interesting backends. I've just used these as a demonstrator. On the left, a couple of my students putting one together for a group of high school students that they were teaching radio astronomy to. So that was kind of the first lesson, was let's go outside. Works really well on a cloudy day because it shows that you can use these telescopes even when it's cloudy. Whoops, that's not what I wanted. After the itty bitty, if you want to go a little bit bigger, I would recommend the Radio Jove project. So this comes out of, a NASA project, and it's been going for, I want to say 20 years. Radio Jove is a kit that you can buy. They send you pieces of the antenna, and the rest you get at a home improvement store. And you build a very simplistic but very cool radio telescope that looks at very long wavelength light. And this is where you can see bursts from Jupiter and also solar radio bursts. So this is a project. So the last picture I showed you of my students playing around with the itty bitty was part of a course that they did for high school students in Manchester, New Hampshire, where they built one of these Radio Jove kits. So they got the kit. We've got 20-foot, I think 20-foot PVC poles in 4 locations. There's 2 copper wires. Those are the antennas. And then they're connected and then sent to a small building. I don't know if I have a picture on the next slide, where we have the receiver. So these students got to build this themselves. The way we did it, we split them up into 4 teams. We had an antenna team, we had a receiver team, we had a data analysis team, and I can't remember what the other team was. Can't remember. We definitely had 4 teams though, and rotated all the students through them. So this is a slightly better picture of the antenna as it sits in at our campus observatory. You can't even see the wires. They're super, super thin. But again, really hands-on project. I think we bought the kit. The kit is fairly inexpensive. That little silver box there is the receiver. You can get, I think it's, no, the receiver somewhere. You can get the receiver pre-built, which is what we did because we only had students for like an hour and a half a week for 8 weeks. They can also send you one that you can build yourself, which again is a really great soldering project. In fact, the students at Lycoming College in Pennsylvania, where I did my undergrad, they built one of the receivers and it came out better, better quality than the one that they had sent to them pre-built, which is pretty cool. So you get your receiver, you can play around, we played around with that in the lab so that the students could understand what was going on. That copper wire is what became the antenna. Students learned, you know, measure twice, cut once, the hard way. Sorry, my dogs are barking in the background. Which is one of the things that I love about these projects, is that they're so hands-on. You get a feel for what goes into the instrument, in addition to seeing what comes out, what cool astronomy comes out. We weren't allowed to let the high school students use power tools. So again, my college students did the power tools while the students watched on. Again, a great range of skills that you get to do with this. Pro tip though, don't try and squeeze really long PVC pipes diagonally into your car so that they're pushing against the windshield. It might crack your windshield. Pro tip, very expensive pro tip. So we got the antenna up. It took us, God, most of a Saturday, I think, to put up. Had the college, again, our college students, they're awesome. They stuck around all Saturday afternoon putting up this antenna. Our first light was really instructive. What you see are a lot of spikes. So we see a lot of radio frequency interference. So stuff from human-made electronics. There's this gentle curve that's happening there. That's actually picking up emission from the Milky Way galaxy, which is one of those things that Grote Reber, all the way back in the day, was able to map with the dish that he built. Those steps at the end are when different poles fell down. So another lesson for us, the original, and this was on me, because I told them I would deal with the mounting issue, how to figure out how to make 20-foot poles stand up, and I did a terrible job. And one of my colleagues helped me figure out how to do that a little bit better. So now I know more about fence posts than I ever thought I would know. What was really exciting is once we got it back up, we took the students for a tour. We actually caught a solar flare, I think the second or third day that it was up. Now, as you saw, there's a lot of interference there. Probably wouldn't have found that flare on our own. What's cool about Radio Jove is there is an email list, a whole community of people that use these telescopes. And so the email went out, said, hey, does anybody see this solar flare? And zoom in on that time, and we caught that solar flare. So the students were able to present that, I think, like 2 days later at their symposium. One step up, this is one I haven't done, but I would like to, is because we're so good at naming things in astronomy, the small radio telescope, which the designs for, I'll have a bunch of links that I'll put in the chat afterwards, but the designs for this come out of MIT Haystack Observatory. This one's a bit more expensive, but you can do cool stuff like map hydrogen in the Milky Way galaxy. So again, all the way back when I was an undergrad, one of my friends was able to, I think, create the rotation curve of the Milky Way as her senior project from one of these. So this is one step up if you really get into it, but I think the Radio Jove is a really good place to start if you want to start playing around with some radio telescopes on your own. This is a list of links. I will post this in the chat because that will be so much more helpful. I can leave it up for a couple of seconds if anyone wants to take a screenshot. There's some other projects that I haven't talked about. A lot of these are geared towards students, often high school students, sometimes college students. The one at the bottom is one I want to point out for everyone, the Society of Amateur Radio Astronomers. Amateur astronomers, I may be biased, but that's obviously like the coolest hobby you could have. Amateur radio astronomers are the MacGyvers of the amateur astronomy world, because you can't quite go and build, buy a telescope and a radio telescope from a catalog. You can, really expensive ones, but most of these are homegrown, home-built. So that's one great place to check out if you wanted to get into radio astronomy on your own. And that's it. You guys can find me on Twitter, Instagram. I'm Noisy Astronomer. My last name's pretty unique. You can usually find me. And I will stop screen sharing so I can put links in the chat and answer questions.
Thanks so much, Nicole. That was an awesome presentation. So we do have a couple of questions. And so we do have about 5 minutes or so for questions. So we'll see if we can get through them all. The first question is, how much background physics or engineering knowledge do you need for that kind of itty bitty radio telescope?
The itty bitty, I've shown to like elementary age kids, and you can also talk to college students about it. You can talk about thermal emission spectra, because when you point at the cold sky or you point at the warm earth, you actually get different signals as well. So you can talk about black body radiation. But you can scale that activity as high or low as you want.
So then, as someone who's familiar with Dark Skies Bright Kids, one of the outreach organizations at University of Virginia, I was curious if you guys had ever done any sort of projects involving radio telescopes like that. And this is just a personal question. If you had done anything with like that in the past, we don't do it now, but I think it'd be very cool to do some stuff with some radio telescopes during.
I'm gonna ask Gail and Genevieve in the
Sure.
who are attendees to jog my memory. I know we did stuff with the infrared cameras.
Yep.
And then we did some stuff with the ultraviolet sensitive beads. Like they made jewelry that would work. So we did some invisible light stuff. I don't remember offhand if we had an itty bitty radio telescope. The pictures I showed you were ones I made when I was a postdoc, but I don't think we did it when I was at UVA.
You guys would be happy to know then we still have an invisible light day that we do, where we do the infrared, the ultraviolet, and we have a cool radio demo that we do as well.
That's awesome.
But anyway, so another question then is, so how many light years away from us could we detect the electromagnetic radiation from a planet and civilization just like us?
Oh
using
boy.
the best technology we have today.
Oh, best technology we have today. So there are some folks either in attendance or possibly your next speaker who might be able to answer that better. I do teach a Life Beyond Earth class, which I also learned from University of Virginia. I've taken that to New Hampshire. And the answer to that depends on, a couple things. If you are looking for a signal from alien civilization, right? It matters. Are you trying to find a signal that they've put out on purpose? Are you trying, so that is really strong and directed in a particular direction? Are you looking to pick up, background signals that are leaking out from their communications? I've seen a couple of figures showing like a little circle, a little sphere around the sun's position in the Milky Way, showing how far out we can potentially detect civilizations, but there's a lot of guesswork that goes into that.
Okay, cool. Then I have one more, just another personal question. So you're talking about being able to observe some of the burst from Jupiter, and so some of my early research involved modeling some of like the electrical conductivity in hot Jupiter atmospheres, with the idea to potentially see like their auroras, like that in their atmospheres. And so I know you can observe auroras, for example, on Jupiter or Saturn or the Earth at these radio wavelengths. Would these telescopes be able to observe at those types of frequencies and things like that too? Do you have any idea? I think it's like 50 megahertz to like gigahertz potentially.
So yeah, I'm trying to, the frequency is correct. The strength is not. So the distance to all these hot Jupiters is going to be well beyond what our Radio Jove could do. But I don't know if that's something that's actually on the radar of like the Square Kilometer Array or something like that coming up. That would be something for one of the big sensitive telescopes.
Right. Okay, cool. So I think that's all the time that we have then. Nicole will be hanging around in the chat. If you guys want to ask some questions that you're thinking about, feel free to do that. You can also ask her, I'm sure, via Twitter or Instagram as well, or her website. But so thank you again for an awesome presentation.
Thanks so much.
Yeah, and so we're going to go ahead and move on then to the final talk of the night. And so that is going to be by Al Wootten. But before we do that, I just want to remind everyone that we only have about 15 minutes left to submit your trivia answers. And so if you haven't submitted your answers for trivia, go ahead and do that. Maybe some people, or when I get a chance during the next talk, I will link, or people can link the trivia as well. And I want to remind people again of the donations to the Blue Ridge Area Food Bank. We appreciate any donations that we can get for the Blue Ridge Area Food Bank as well. And so now what I'm going to do is I'm going to go ahead and introduce Al. And so Al, you can go ahead and turn your video on. Not quite share your screen yet. I'll let you know when you can share your screen. That's a great view that you got there, Al.
Astronomy used to be done at night.
Right, exactly. So Al Wootten, aka Astral, has been working on the ALMA telescope, for which he's now the North American Deputy Program Scientist, and working on science results, currently molecular globules in the Crab supernova remnant, and defining instrumental upgrades to sustain its scientific output. And Al is a scientist at NRAO and a research professor at the University of Virginia. And so Al is going to be talking to us tonight about ALMA. And so you can go ahead and take it away, Al, and you can go ahead and share your screen whenever you'd like.
All right. Okay, did that work?
Yep, looking good from our end.
Okay, so Matt already told you everything on the slide. ALMA is a NSF project. NSF has a contract with Associated Universities Incorporated to run the National Radio Astronomy Observatory, which manages ALMA for it. Okay, so what are we interested in here? We're interested in the millimeter and submillimeter spectrum. So here we have wavelength all the way from optical out into the millimeter. Why did we want ALMA to look at the millimeter submillimeter spectrum? Well, you can see three spectral energy bumps in the spectrum of the universe. There's a cosmic microwave background over on the right. That's the strongest. This is the Big Bang radiation, redshifted by billions of years. In the center is the cosmic infrared background, which we didn't know about until the IRAS satellite was launched in the 1980s. But as you can see, it has a substantial fraction of the light in the universe. And on the left is the cosmic optical background, which has all the stars and everything. So as you can see, the photons on the right, the millimeter, submillimeter photons, are the most abundant photons in the cosmic background and in the spectrum of Milky Way and most spiral galaxies. So if we could make a telescope that could look at those, we'd be in great shape. So ALMA provides this telescope, a probe of tremendous ancient galaxy building star formation episodes. And the ALMA range goes from 1 centimeter to about 0.3 of a millimeter. Now 1 centimeter is about the shortest wavelength the VLA operates at. ALMA goes to much higher frequencies, much shorter wavelengths, and covers both components in the atmosphere as much as the atmosphere of the Earth will allow. Let's see, whoops, there. So there's the ALMA range. It's an international partnership of 23 countries, I'll talk about a little later, but much of it was built in Charlottesville. Where is it? It's in Chile. So here's a map of South America. Most of you are probably familiar that Chile is the sort of skinny little country off on the western side. If you go to Chile, you'll go to Santiago. Santiago is a nice, lush, green place. That's why there's 8 million people there. The other observatories are also in Chile because it's very dry, but they're to the north. So Cerro Tololo, the other NSF optical observatory, is to the north. Paranal, ESO's flagship observatory, is also to the north. And then in the panel on the right, you can see a blow up of that upper area. You can see ALMA is off in a little finger that sticks in between Bolivia and Argentina. Okay. ALMA's about 20 years old. Here's a picture of me pounding in a spike for the first antenna pad for the center of the array. 20 years ago, as you could see, there was nothing at all there. If you approach the site, you get to the Salar, the Great Salt Lake, into which the snowmelt from the Andes empties and evaporates away. And from the highway that runs along the eastern side of it, you can travel up to the ALMA site, which is the little white area on the right.
And then further up, the twisty road that you can start to see up to the ALMA site at 16,500 feet behind those mountains, which go up to over 18,000 feet. We don't run ALMA from 18,000 feet for a number of reasons. Here is the operations support facility at 9,500 feet. We've got to generate electricity. If there's no oxygen, electrical generation is not very efficient. So we generate the electricity at the operations support facility. That's also where the signals mainly go to go out to the world. It's where we store the data. 16,500 feet is too high to have the normal kinds of disks. You have to have solid state disks because there's no air for the heads to float on regular disks. So the operations support facility is a fairly large complex. There are about 200 people who work here to run ALMA. The observations take place in a little room that's lit up on the lower right over there. And the receivers, the correlator, all the maintenance is done in this building at a more reasonable level. So ALMA, we wanted to have an antenna which was very sensitive and very large. So as with the VLA, we broke the antenna surface of a 16-kilometer telescope up into a number of smaller elements. In ALMA's case, there are 54 actually, 12-meter antennas and 12 7-meter antennas that we use to provide the signal. Now, as the Earth rotates, this whole structure spins just like it does with the VLA, and it sweeps out arcs on the sky, sampling all the spatial information that we need to recreate an image of the source of the sky. Okay, so the aperture is covered in time by moving the antennas to other foundations. We have 192 of them, or by Earth rotation, Okay, so here is a picture of the some of the antenna stations. On the right, you see the compact configuration where we can fit them all within about 150 meters. And so, you know, the aperture is about half filled with steel. At that, these antennas are so close together that they only miss each other by a centimeter when you steer them. And the upper left is a more extended array, and then the most extended array is out to 16 kilometers in the lower left. As you can see, it's no longer in a nice regular pattern because there are mountains in the way. Some of those mountains, 8,000 feet, a little hard to, 18,000 feet are a little hard to move. So we have to have a staggered configuration, a large one. It's difficult to operate an interferometer where you have to move the antennas out that far. Here is Santiago. It's about the size of Washington, D.C. Washington, D.C. is 15 kilometers on the side, and here's the size of that extended array compared to Santiago. Up in the upper right is Vitacura, where the actual Santiago headquarters of ALMA is. Okay, so here's a comparison between visible and sub-millimeter radiation. And so at the top, we have a little chart that tells you whether it penetrates the Earth's atmosphere. You can see the visible light here does penetrate the Earth's atmosphere. I'm sitting out here looking at stars right now. The wavelength is about the size of amoebas. But over in the microwave region, about the size of the pinpoint here, where ALMA operates, the radiation does not penetrate to the surface of the Earth. And that's because of water vapor. But the water vapor disappears by a factor of 2 for every 5 kilometers up you go. So if you're, for every few kilometers up you go. So when you're at 5,000 meters at 5 kilometers, it's much, much less. So here's the ALMA range in yellow. And at the bottom is a thermometer telling you where at what temperature the spectrum peaks for these various things. So you can see in the optical, we're looking at a few thousand degrees. When we look at the sun, at ALMA, we're looking at a few hundred degrees when we're looking at a black body or a normal object. So ALMA, and I'll go over this again, so I won't belabor this, is a cooperation between many countries. Europe, East Asia, Republic of Chile, and North America. So when we built ALMA, it was 100 times better than anything that had gone before. We had the best site on Earth, high in the Chilean Andes. Maybe there's a site in Tibet, which is almost as good, but there are a lot of political problems with building a telescope there. It has the highest performance antennas and receivers available. We beat what was available in the world by a sizable factor. We built ALMA, and it has enormous collecting area, 6,500 square meters. So if any of you have been over to Greenback, it's about the size of the GBT, but of course, you know the problem of the GBT is a gigantic structure and you can't make it work at submillimeter wavelengths. So we cover the atmospheric window from 1 centimeter, the shortest wavelength at which the VLA operates, all the way out to 0.3 of a millimeter. And by doing that, and by going out to 16 kilometers, we get an improvement of resolution over what we had before by 100 times. So what does that look like? Somebody asked a question a while ago of whether we could see planets. We can't see planets really because they're too small and the flux goes as a very high power of the radius. But when they're big, when they're small, when they're growing, we might be able to see them. So the first thing that happens to make a protostar on the left is a cloud of gas and dust begins to collapse. It collapses, of course, as it collapses, it carries the angular momentum with it, just as a ballet dancer can, or an ice skater can spin up when they draw their arms in, things spin faster and faster, and you have to lose that angular momentum somehow. So the way that happens at a star is it emits a jet. These jets were discovered 40 years ago this month at the Millimeter Wave Observatory at the University of Texas. Some material, however, stays in the disk and keeps rotating, and that's the material out of which the planets will form. So on the right, this is all theory now, you see a protoplanetary disk, which has some junk in it and little planets forming. So this is what we thought it would look like. And in the end, you have the solar system on the right with a star in the middle and planets around it. What do we actually see? Well, this is what we saw before ALMA came along. All we could see was blobs, basically. These are some areas where we thought there were protoplanetary disks because we could see dust and molecules near this star, but we couldn't really get a good view of them. When in 2014, we moved ALMA out to its longest baselines and started taking images, this is what we saw. Protoplanetary disks, just as we had expected. They have little grooves in them. Now, what are these grooves? In the cartoon that you saw, these were like little racetracks where the planets are all moving along, sweeping up matter out of the dust, which is what you're looking at here. There's also gas in these disks. There's much more gas than there is dust, but it's much harder to see. I'll show you pictures of that in a minute. So this was like a holy cow moment. It's seeing exactly what we had hoped it would see. Well, that was 2014. Many years later now, we're seeing all kinds of things. So here is a suite going from left to right of dust images of various young stars and their dust disks. And going up to down, what we're looking at is the molecular gas associated with these. Well, look, it has nothing like the same shape as the dust disks. The dust disks are concentrated into the center. The gas is spread further out. There are good reasons for that. I won't go into the physics for that here. But as you can see, you could look at many different molecules as they're faint, but you can map them out. So usually what we do is look at CO. I think the bottom line there, it's all obscured by my pictures, is C18O, a rare version of CO, and it's the most compact, but it's still not as small as the dust. Here is RU Lupi, which has a huge gas disk. This is a carbon monoxide image of RU Lupi. This is 1,000 AU across, and that dust disk with the planets and the racetracks in the center is just this little tiny thing in the center. So there's a huge amount of detail in many of these objects. Can we observe planets? Well, here's an example of planet formation in some of those protoplanetary disks. The object PDS-70 is a 5 million year old small, sort of like the sun type star, 110 parsecs distance. So it's surrounded by dust rings at 10 AU and at 74 AU. Here's the 74 AU one. It's the big one over on the right. That's a long way out. Remember, Jupiter is at 5 AU in the solar system and Saturn is at 12. So these are a long way out, but there's a big gap in the middle. In that gap, the very large telescope that ESO runs at Paranal detected Jovian mass planets B and C. When we tried to image these with ALMA, we couldn't see C, which is presumably doesn't have any dust associated with it. And so I said its emission goes as R to the 4th, so it doesn't have a very big radius, so it's very hard to see for us. You can see it by reflected light, easier than emitted light. On the right is the VLT sphere image, which shows us reflected light from the surface of the disk. When we look at this with ALMA, you can see that the PDS, whatever it is, 70B shows dust trailing it, but PDS 70C actually has mass associated with it. What we think is that this is the dust still being accreted onto a newly formed planet, which only has a mass of 2,000ths to 4,000ths of a solar mass. On the lower right is HD 100-546, a BE star, a much more massive star, about the same distance. Here we see a different feature that allows us to see the planet. So as the planet moves in the gas disk, it leaves a wake behind it, just as a boat moving on the water out here behind me leaves a wake. And by looking at the red shifted and blue shifted components of the gas, you can see that wake as we see in the lower right. You can see a little blob here of red and a little blob of blue. This is a very difficult observation to make. And so we're trying to make ALMA even more sensitive so observations like these can be more common. So yes, we can't quite see the planets, but we can see their signature in the wake that they leave behind them. So maybe you're not happy seeing that there are boats out on the ocean by the fact that they leave wakes behind them, but it's the best we can do right now. But ALMA can also probe the creation of galaxies. I'm just going to skip over this slide. Very complicated carbon monoxide associated with galaxies. But ALMA is powerful enough to see lots of galaxies. Here are over 100,000 CO clouds. Each of these CO clouds has masses of many solar masses, hundreds, thousands of solar masses in it, and 6 dozen galaxies. So you can see we can take a census of those clouds in which stars form, and planets may eventually form too. So this is data that's not, it's been released in press release form, but the papers are still coming out. Furthermore, ALMA can look at the creation of the elements. The first stars created oxygen, carbon, nitrogen. Supernovas disperse those. That's what the dust and the gas is made out of. ALMA has imaged the most distant oxygen, carbon, and nitrogen known because ALMA observes very highly redshifted material that's redshifted all the way into its portion of the spectrum. So on the right, we can see oxygen 3 emission was detected from this object A2744YD4, which was emitted when the universe was only 600 million years old. Stars had to create that oxygen. Those stars had to spew that oxygen through supernovae into the interstellar medium. And so the estimate is that that oxygen was formed from the first stars and is the oldest oxygen in the universe. So ALMA is a story of astronomers and engineers worldwide having come together to build ALMA, an observatory that harnesses the efforts of many nations in order to produce its science. It couldn't have happened with only the United States or only Europe or only East Asia. And of course, we needed the site in Chile. So it really required all these countries, the 23 countries involved, to come together. Okay, so I'm going to just leave it there.
Great, thanks so much, Al, for an awesome talk on ALMA, all things ALMA. And so if you go ahead, you can stop sharing your screen. We'll do a little back and forth. We have time for about 2 questions.
Okay.
And so yeah, so you can go ahead and just stop sharing your screen.
It's dark out here.
Yeah, the first question I had for you is if you could explain to everyone where you are right now and what you're trying to observe.
Well, I'm here watching Perseus rising, trying to see if I can see some meteors. I can see Vega. I can see the summer triangle over my head, but I can't see much of Perseus right there. A few clouds over in that direction. So I'm down on at the mouth of the Rappahannock River at our house down there. As you can see, there's not much to see here on the ground. A few lights in somebody's dock.
Okay, so then, so two questions then. The first one would be, so why are we looking for planets so far away instead of focusing attention closer to home? So why is ALMA looking for planets so far away?
Well, there's no way that we could see a planet like Jupiter, Saturn, or the Earth with ALMA unless it's nearby. And so what we've got to look for is an object which is both nearby and in which those planets are bloated by the material which they are still accumulating. So what we can see are circumplanetary disks, but not the actual planets themselves, because those disks have a large radius, or flux goes as r to the 4th. So you really need to get them big before you can see them nearby. So there is one star formation region, TW Hydra, is located just some few dozen parsecs from the Earth. And so we have concentrated on that disk to try to find something, but so far no planets there.
Okay, great. We actually had a couple more questions roll in. So we have some time. We don't have a sharp cutoff at 9, so I'll be able to ask maybe two of these other ones as well. But one of the questions was, in a census of planetary disks, is there a different frequency of planetary wakes the further away in space or back in time you look?
Why?
I guess the question would be, is there different frequencies maybe you would observe these different wakes as you look farther away in space or farther back in time?
Well, I should say that's the cutting edge of where the science is right now. There are only a handful of those wakes that have been detected. Right now, the sensitive, so the wake is only seen in, most of those disks you saw were in dust. Dust emits all across the spectrum. So you can just make the spectrum that you integrate over larger and get a brighter signal and be able to do better with the dust disks. Molecules, on the other hand, which you have to look at to be able to see the radial velocities and get those wakes, only emit over a very sharp little region, like a radio station or a TV station. And so you have to be able to have incredible sensitivity to be able to see them. And so only a few disks have had those radio velocities measured yet to the degree of accuracy you need in order to see the wakes. So yeah, we're trying to improve the sensitivity of ALMA, but short of building another 100 antennas, which would cost a lot, it's a difficult trick.
And then the final one we have time for, and maybe Al can answer some of those questions as we go through the end of the event. But the final question we have time for is, are the wakes more likely to be made of certain gases or elements, or does it more depend on what the instrumentation is meant to look for?
Well, okay, so if you're looking for a wake behind a boat, you could look for a wake in the water, where you'd have a good chance of seeing it, or one in the atmosphere, where you'd have zero chance of seeing it. So yeah, it depends on the molecule you're looking for. And the molecule of choice is usually carbon monoxide because it permeates the disk and it's bright, and so it's easier to see than another, like some of those other molecules I showed you in the slide. I think one of them was HCN, hydrogen cyanide. That's just too weak. You have a hard time seeing the wake in HCN. So it's almost, right now, it's almost always carbon monoxide.
Okay, great. Well, unfortunately, we don't have any more time for questions, but maybe Al will stick around in the chat for the final few minutes that we have left to answer some of those questions. Sure. And we're going to go ahead and wrap up our first virtual event. And so what I'm going to do is share a couple of slides. We're going to go over the trivia. And so let me go ahead and share my screen now. All right, and so I just want to remind everyone of this donation link that we're trying to do. So we're trying to, rather than collect donations for our typical Astronomy on Tap events, to fund our prizes and ability to rent out spaces and get drinks and food for some of the presenters. We're hoping we can donate to some local things in the Charlottesville and Albemarle County area. And so if you can donate at the link attached here, and hopefully someone can send that in the chat, we'd appreciate any of the money that you can send along. All right, so now let's go over the trivia questions. So we have closed the trivia. We'll be contacting some of the winners and some of the random, picking some random people to send some prizes as well. So if you missed seeing Comet Neowise this July, don't worry, it'll be back in 6,800 years. So don't imagine anyone will be around to see Comet Neowise again. And question 2, many trillions of particles speed away from the sun as the solar wind. How much mass does the sun lose each second? That answer is 1 billion kilograms each second. I think I counted the zeros correctly there. Which of these constellations is not part of the astronomical zodiac? And that is Orion the Hunter. And so Fucus might be one of the other ones you guys didn't recognize, but that's one of the more modernly been added to the astronomical zodiac. SpaceX's Dragon capsule is named after which fictional creature? That is Puff the Magic Dragon. If the Earth were the diameter of the rotunda, the sun would be 1.6 miles in diameter and located at Pittsburgh, Pennsylvania. That's how far away the sun would be if we shrunk the Earth to the size of the rotunda. In the constellation Perseus, some depictions show him holding the head of what enemy? And that answer is Medusa. Seen holding the head of Medusa. ALMA is the name. Oh, so this was actually our Facebook hint for the night. So if you guys haven't yet, make sure to like us on Twitter or make sure to like us on Facebook as well. We're AoT-Cville on Twitter and just facebook.com/AoT-Cville on Facebook. But ALMA is the name of an observatory, but it also means, appropriately, soul in Spanish. Carl Jansky observed the first cosmic radio waves in 1932 by accident. While trying to minimize static in his radio antenna, he observed what astronomical object? And that was Sagittarius A star, or the black hole in the center of the Milky Way. There's currently a train passing by outside my apartment, so hopefully you guys didn't hear that too loudly. The discovery of Neptune is credited to Johann Galli in 1846. However, Galileo observed Neptune in 1613. Why does he not get the credit? Well, that's because he thought Neptune was a star. In fact, if you guys were to look at Neptune either through binoculars or you would probably see that it would look like a star as well. Astrological ages are not clearly defined, but one interpretation says the dawning of the age of Aquarius, I won't sing this time, happened when the first 6 planets, the sun and the moon, all aligned with the constellation Aquarius. What was the date of this event? That was February 4th, 1962. So hopefully you guys did okay on the trivia, and we'll go ahead and reach out to some of the people that performed well and some random people as well. And so finally, the last 2 slides I want to do to wrap up the event is ask you guys for some feedback. And so we've had over 100 people tuning in tonight, which was an absolute awesome showing. We're certainly going to be putting on more virtual Astronomy on Tap events in the future, hopefully once a month moving forward, but tune into our socials to find out when that happens. But hopefully some of the astronomers appreciate this joke at the top because in addition to its astronomical significance, feedback is going to be essential for us to make Astronomy on Tap as great as we can. So if you can provide feedback to us at the links that are attached in the chat, it's just a Google form. It asks you a couple of questions, should be really easy to fill out. It'll help us make Astronomy on Tap great for the future. Provide any suggestions that you can think of to make our event more fun for you. And so the final thing I want to do is just give a couple of thanks. And so this event couldn't have happened without a large amount of people. And so the first thanks I want to give is to Albemarle Ciderworks for their awesome tour of their facility, and then for the cider as well. It's been awesome. If you guys want to order some cider from Albemarle Ciderworks, just make sure to check out their website. The speakers, obviously, Ed, Nicole, and Al. Some volunteers, Molly and Allison, were able to create the trivia, create the Google Forms. So thank you for that. And then Katarina was live tweeting the event. So hopefully you guys were able to check that out on Twitter. I want to thank some of the organizers. Special shout out to Catherine and Brett for helping behind the scenes, and Catherine for helping a lot for the organization of the event and for advertising the event as well. And then Marilyn, Whitney, and Scott, of course. And then final, of course, we give a thank you to all of you who tuned in. I thought it was a really awesome event. I had a lot of fun. I hope that you guys had fun. I will be checking out some of the chat. If you guys want to send some thanks as well and some appreciation in the chat, that'd be great. And for now, hopefully we see you at our next event, and tune into our socials to see when that next one will be. It'll be in about a month or 2. So I'll see you then, and thank you guys all for tuning in. And cheers.